So in the previous slide, we learned ISOMAP and LLE, and these two algorithms are kind of representative manifold learning algorithms. And we use them a lot, and there were lots of papers about these algorithms. But recently, instead of these two algorithms, SNE or TSNE is more popular. So whenever you need demand reduction for your application, like for visualization, then try SNE or TSNE. Okay, so let's talk about TSNE or SNE, which is a stochastic neighbor embedding. Okay, and the previous manifold learning algorithms, ISOMAP and LLE, they emphasize local properties. So we actually checked the neighbors. In ISOMAP, we used the geodesic distance based on the neighbor information. And in LLE, we actually try to preserve the neighbor information, right? But in those algorithms, infinitesimal distances are not infinitely important. So even though the point is really close to me, that is not that important. Okay, it's just one of neighbors. Okay, so in SNE, we consider the close point more importantly. So let's talk about stochastic neighbor embedding. It actually probabilistically decides if points are neighbors to a given point. And the algorithm is following these steps. First, we convert the similarity into the probability, or we convert the distance into the probability. And then neighbors are selected probabilistically. And then we use the distances in a low-dimensional space which define probabilities. So in a high-dimensional space, we have points, and then we use this distance to define the probability. So now we have a probability here. And then in a low-dimensional space, we have, this is x, and we have y's. And then we can define the probability too, right? And then we actually compare this probability, and we can actually measure how similar these two probability distributions are, right? So to measure that, we use Ka divergence. So we compute K divergence between the two probabilities, and then we minimize K divergence with respect to y sub I. So we actually change this y to make this distance to be minimized. Okay, so then the distribution actually defines how the samples are distributed. Okay, so in the high dimensional space, this probability is fixed. We can fix this probability. And in the low dimensional space, depending on how these y samples are distributed, py will change. So we want to minimize K divergence. By doing that, we can actually change the location of the y's. That's the point of SNE. Okay, so let's go through these equations. And don't get fooled by these many equations. These equations are just the simple equations, okay? So first, we have to define the probability. The probability of picking x sub j as the neighbors of x sub I, and in the high dimensional space. So how do we define this probability? Actually, we use a distance first. In this case, it is just the Euclidean distance, or if you want, you can come up with other kind of dissimilarity, but let's say just the Euclidean distance. And then this is our distance square. And when we have a distance, then we can define the probability in this way. And let's focus on this numerator. And in this case, if the distance is large, so it's far from each other, then we put the minus, so we take an exponential function. So if the distance is large, then the probability will be small. And this part, this denominator is just simply normalize this term to be probability distribution. So now we have a probability for j given I. Okay, so this means from I's perspective, the probability of j as a neighbor is defined by this. And then we have to define another probability in a low-dimensional space, right? So the probability of picking y sub j as the neighbors of y sub I in a low-dimensional space is defined in this way. Okay, so this one is almost the same as this one, except normalization term, sigma sub I. Because in this case, given x, we don't have any idea about the scale of x. But in this case, we can actually control the scale. So the sigma for y, sigma in the low dimension space is supposed to be just 1. So we can ignore that. And then except that these two is almost the same, right? And in this equation, d sub ij square is defined in this way. It's basically the same thing. And then now we have two probability distributions. And then we have to define the k divergence between this probability and this probability. And this is our loss function. Actually, in this loss, we consider all the samples. Okay, so we have a summation here to consider all the samples, and we actually check the k divergence of all the samples here. So which means all the samples should have the same kind of neighbor distributions in high dimension space in the low dimension space. And if we rewrite this k divergence, then this is it for a sample I. And if you look at this one, the p of j given I is kind of the weight, right? So if the sample j is really close to sample I, then we consider this as a more important neighbor. Okay, then how can we actually train the primaries? So we have a k divergence objective function. What should we do? Since that objective function is not analytically solvable, so we cannot solve that, so we can actually use iterative solutions like a gradient descent method. When we have objective function like this, then when we start from here, okay, then we just take a derivative. If the derivative is positive, then we can move this parameter to the left side. If the derivative is negative, then we move the parameter to the right side. This is how we learn the parameters based on the gradient descent method. And we're going to talk about this optimization later in optimization chapter. But that's basic idea of this gradient descent method. So to use this gradient descent method, we have to get the derivative. Okay, so in this problem, the parameters are y sub I. And then we just take a derivative of this loss with respect to y sub I. Okay, and then this is just a simple derivation, and then we have this one. Okay, now we have gradient information, then we can train these parameters. We can update this y sub I for all the i's. Then we can rearrange the samples in the low dimension space. This is how SNE works. Okay, and then SNE is not a convex optimization problem. Do you remember the isomap and LLE? They were based on the eigendecomposition. So we actually solved the problems without any iterations. Okay, because the problem is really simple. It was just a convex problem. So just eigendecomposition would be possible. But SN is not. It's more complicated. So we use gradient descent method to update the location of the samples in a low dimension space. Okay, so I just talked about SNE, but instead of using SNE, actually, practically, we use TSNE. So in this slide, we're going to talk about TSNE. And actually, in sklearn, we have TSNE, so we're going to use TSNE in this way. But let me tell you what's the difference between SNE and TSNE here. And TSNE is a symmetrized version of SNE with T-student or T-distribution instead of Gaussian. So first, it's based on symmetric SNE. So in the previous slide, we have this gradient information with 2 and PJI, QJI, and PIJ, QIJ, because PIJ and PJI, they are different. These two are different, but if we assume that these are the same, so if it is symmetric, then we can ignore the second part and then we can just multiply here. Okay, so this is the symmetric version of SNE. And we use a T-student instead of Gaussian. So this is a T-student. Then there's a question. Why do we use a T-student rather than the Gaussian? So let's talk about T-distribution first. Okay, T-distribution is a sampling distribution like a distribution of sample mean. Given n samples, the sample mean and the variance are given by this. I think you're already familiar with these definitions. So we have n samples and the sample mean is just average and the sample variance can be calculated in this way. Okay, and then the T distribution is about the distribution of averages. So let's say we are interested in the height of Korean people. Then we can just check 1,000 people's height and then we can get the mean and the variance. Okay, then if we assume that the distribution is Gaussian, then that's it. Okay, we have a mean and the variance, sample mean and sample variance. But what if we have 100 samples and another 100 samples and another 100 samples? Then we can calculate the average and variance from these samples, and then we can calculate the average and variance, and we can calculate the average and variance. Then this average is represented by the T distribution. Okay, so this is the distribution of averages. And then this graph summarizes T distributions. If we have just one sample in this set, then we have this yellow graph. And if we have just two samples, then we calculate the mean and the variance, mean and the variance, mean and the variance. Then this average will make this purple one. And if we have infinitely many samples in this set, then we have Gaussian. T value is defined by this one, and this is actually the distribution of T values with a different number of samples. And the important thing is that the T distribution is lower and wider than Gaussian with more probability on high values. So look at this one. This one is Gaussian. The black one is Gaussian. All the other T distributions are lower than the Gaussian. So this one is lower than the Gaussian and wider. So this is T distribution. This one is Gaussian. So this one is wider, so that we have a more probability on the high values and the low values. So again, T distribution puts more probability on the higher values and low values compared to the Gaussian. Okay, so let's get back to this slide. And we use T distributions because of this reason. So TSNE overcomes the crowding problem. What's the crowding problem? So when we actually project the high-dimensional samples into the low-dimensional space, then low-dimensional maps are not large enough to represent nearby data points. So this one is connected to the cursive dimensionality. So in the cursive dimensionality, if we increase the dimension, then we need a lot of more samples to be dense enough in the space, right? So we have a fixed number of samples in high-dimensional space, and then we project all the samples into low-dimensional space. So it's kind of exactly opposite of this decursive dimensionality. So in the low-dimensional space, relatively, we have too many samples in a smaller volume. Okay, so there are lots of overlaps here. So since the volume is relatively small, and there are lots of overlaps in the low-dimensional space, so the samples push each other. Samples push other points away. So the data points will be placed too far away in the low-dimensional space. And then the probability Q of J given I decreases. When the two samples are far away, then the probability is low. So if they go further away, then this probability decreases. this is the problem, because this one, P of j given I, is fixed from the high-dimensional space. And then this one is decreasing when the samples are far away. So this one is high and this one is low, so this will be positive for all pairs, and they generate attractive force between all pairs. So even when the 2 points are really far away, but there are strong positive force to pull them each other. So T students gives more probability to the long distance pairs. So if this one goes high, then this one, P minus Q, will be smaller. So it could be 0 or it could be sometimes minus. But anyway, the distance between these two probability will be small. So it prevents attractive forces between two faraway pairs. That's why we use a T student here. So this one is fixed. And then Q is a T student to solve this crowding problem. So crowding problem means the samples in a low demand space are too crowded in the space. When we use this TSNE from sklearn, it's simple. So just import TSNE, and then this one, X is 4 by 3. So we have 4 samples and 3 is 3 dimension. So from the 3-dimensional space, we want to project the samples into 2-dimensional space here. And then X embedded will be 4 by 2. We just change the dimension from 3 to 2. This is simple. So when you have your own data set, then just import the TSNE and then call TSNE with the fit transform function. That's it. And this is the result of isomap, LLE, and TSNE on the MNIST digit directly. So compared to isomap and LLE, TSNE finds more separable classes. And this is not perfect. As you can see here, there are some digits in the wrong class. But still, compared to isomap and LLE, TSNE is much better. So far, we talked about isomap, LLE, and TSNE. And there is another approach for nonlinear dimension reduction. Okay, so it starts from the data representation. Yoshua Benjo said data representation assumes a manifold of the variations. And the manifold learning is actually a nonlinear dimension reduction method. And there is a limit in the previous method, like isomap and LLE and TSNE. So they do not scale well with sample size. So basically, they scale quadratically with the size. So in isomap and LLE, when we have n samples, then they have to solve eigendecomposition of n by n matrix. And in TSNE, we don't have eigendecomposition, but in the loss function, we have a sum of all the samples. And another problem is that the training data is referenced for test data, so we cannot throw them away. So we have to keep all the training samples for the test data. Okay, that is another problem. The reason why these methods have this limit is that they are non-parametric method. So to overcome these limits, let's get back to parametric methods, parametric models, especially neural networks, like a self-organizing map or restricted Boltzmann machines and autoencoder and so on. And in 2006, Jeff Hinton and his student actually had one paper published in Science about autoencoder. So they actually stacked many autoencoder layers, and then with this deep autoencoder, they achieved really good performance of nonlinear dimension reduction. Okay, that was the beginning of deep learning era. We'll talk about neural networks in detail in the neural networks chapter. Okay, this is it. Thank you.